First of all, I would like to thank the organizers for inviting me here to this beautiful spot and to this wonderful meeting. It's really quite inspiring with these different things coming together, and I had a very nice time here, and I hope you will also enjoy a little bit what I'm talking about today. And yeah, high quality freestanding magnon nanoresonators. Maybe I mentioned just in the beginning, this work has been seen some funding. Basically, it started in a European project called IFOX, and it's still going on in our collaborative research center on oxide interfaces. And the people involved in this work, mostly from my work group and from the Center for Material Science. So you can see here Frank Heiroth and Frank Syrowatka. He started the development of the electron beam lithography. He's doing very nice SEM pictures. Philipp Trempler, this guy, he continued. Philipp Geyer did the simulations that you will see. Christoph Hauser, where is he? Up there. Christoph Hauser did some PLD growth, and also other groups at the university were involved. So Georg Woltersdorf and Ruven Dreyer, they did the optical measurements, and Stefan Ebbinghaus prepared our very special YIG targets for the PLD. So anyway, what I want to talk about is firstly a brief introduction why we might need YIG nanoresonators. Some of it has already been given yesterday by the nice talk by Kanming Hu, and then I will talk about how you can make them, and finally show that we can make them and what structural properties they have, and especially what magnetic properties they have, because it's quite interesting, and the outcome of these experiments was even for us a very big surprise. So I will probably go pretty fast through this. So there is this area of magnon mechanics which was already introduced yesterday. So for example, it has been shown that you can couple qubits to magnons, and also it has been shown that you can couple qubits to mechanical oscillators. That's another point which has not been stressed so much yesterday, but Kanming Hu showed you could transfer between all different kinds of systems. And we're especially interested in the coupling to mechanical oscillators. And one way to do this coupling, if we can already couple qubits to magnons, would be to use the magnons to couple to mechanical oscillators, if we can have a nice mechanical YIG oscillator, and use the magnetoelastic coupling. I mean, in principle, this has been shown. However, you can see this is one of these oscillators which has been used for such an experiment. And the problem is these oscillators are almost a millimeter big. So, I mean, one reason is certainly that, as Kanming Hu also mentioned, you need a lot of material to do this experiment. But anyway, if somehow you want to make more complex systems, you need some way to integrate things, and you cannot integrate millimeter-sized YIG balls, but for a complex experimental setup, you need something small. And you need something which has the right frequency. I mean, here it was basically the eigenfrequencies of the oscillation of this ball, but you know better than I do that you can make resonators which with all different kinds of frequencies. And yeah, as I said, the problem is the smallest spheres being used up to now are 250 micron, and we want something which is smaller than this. Here, by the way, you can see these mechanical modes, the oscillation modes of the balls which have been used. And but just to see whether we can match the frequencies, I think a very good example are these small oscillators, which are basically simple bridges, already fabricated in 2003 by the group of Michael Rukas, and he showed that actually you can get the mechanical vibration frequencies of these oscillators into the gigahertz regime. And the gigahertz regime is basically where we can do nice experiments with magnons, although 1 gigahertz is still quite low, but maybe we can get higher than this. At least YIG can be quite solid, and so we might expect that we can get to high frequencies with this material. So this was just the introduction, and now the question is, how can you make these resonators? And although we have seen a lot about how to fabricate resonators, I still want to talk a bit more about it, because how you do it strongly depends on what you want to have in the end. If you want a single resonator to go somewhere and do some measurements, like an AFM tip, for example, or like these very nice wires for the NMR measurements, then you're basically free to choose however you do it. The important thing is that you have one working device in the end. But this is not what we're looking for. We want to have something where we can put lots of oscillators close to each other, and we need also to preserve the properties. I mean, normally you look for mechanical resonators where you just want them to be mechanically stable to have the right properties, but in this case we also want the magnetic properties to remain the same. And YIG is a crystalline material, and if, for example, you use ion milling or focused ion beam, it can well be that you damage the material, and if you make a very small device and you damage the material, then it's quite likely that the physical properties will degrade. But one standard process in principle to make resonators out of crystalline materials, or to make 3D structures out of crystalline materials, is the following. You have normally epitaxial growth at high temperatures. I mean, we don't get bulk YIG crystals out of which we want to cut this, but we grow the stuff. And when you have epitaxial layers, then you cannot do any patterning by resist and lift off, because the resist that you use is normally not stable at high temperatures. You can use some solid state resist or shadow mask, but in this case you have problems to remove it afterwards, and to make nice processing you want this. So normally what you do is you use a sacrificial layer underneath. Here, for example, you see this is the sacrificial layer. The red layer is the one out of which you want to make your resonator. You put a mask on top, and then you do some dry etching going down here, and then you can remove the sacrificial layer underneath, and then you have your resonator. So this is standard stuff, and you can get devices like this, for example. You can also use focused ion beam. I mean, it's quite clear you can do it, but the use is limited, because you're always restricted to certain shapes, because you still coupled to the substrate, and that means somehow you have to etch from the side. I mean, there has been one result from the Saito group, but you can see this resonator had about 80 micron length, and the resonance frequency was in the kilohertz range, so upper 100 kilohertz range, but still not at all what we want to go for. And again, you see, if you do it by focused ion beam, then you get this, this pit underneath. And for future integration, this pit is not very useful, because you have to go over the edges. And so you want to do it in a different way. There are also other processes, but they are based on lift-off. And then you need low temperature deposition. But it has been demonstrated first, I think, by Diana Mahalou from the Weizmann Institute. She developed a multi-layer process using resists with different sensitivity. And if you do this, then you can make these kinds of bridges. These were fabricated when I was in Würzburg. We had a lady there who, let's say, she adopted the process, and she was quite fast. It took her 48 hours to make these bridges after she got the recipe, but she said, they don't look nice. So she developed another process which is based on different acceleration voltages, and this looks much nicer. But this is metal, that's the problem. But you can make very long bridges, so these were still limited in size. Here we can go to something like 10 micron, and we can also make complex stuff. So how does this help us? I mean, in the end, if you want to use the sacrificial layers, it doesn't work, because for YIG you don't have them. So the problem is YIG is a garnet, and garnets grow on garnets, or on other garnets, but on nothing else. And garnets are very difficult to etch, especially by wet etching, and there's a high probability that if you can etch the substrate, you will also etch the YIG. So this doesn't work. And also, if you use the standard deposition techniques like liquid phase epitaxy or pulse laser deposition at high temperature, you cannot use this lift-off process. So how can you combine lift-off with crystalline YIG? And there, already some time ago. We had a kind of breakthrough, although we didn't understand how far this would actually go, because we did some YIG deposition by pulse laser deposition at room temperature. And this way you deposit amorphous YIG. You can see here transmission electron microscopy images, and the Fourier transform shows you that there's some order, but it's not a crystalline order. However, if you anneal it, it looks like this. We were not able to find any defects, not even at the interface to the substrate. So this is GGG and YIG, so standard system in principle. And you see perfect crystallization over at least 100 nanometers in this system. And the substrate in this case acts as a seed. And these layers have astonishing properties, because normally we have already seen some values. So if you grow YIG at high temperature by PLD, you make thin films, you usually get into a range for the damping of, let's say, if you're good quality, then you have 4 times 10 to the minus 4. If you have very nice quality, you maybe get 3 times 10 to the minus 4, maybe even slightly below. And you usually have a line width of a few Ørsted. So you're happy if you have 3 or 4. And in this case, what we found, we have a line width, so this is the measured line width from the diagram of 1.5 Ørsted. So this translates to 1.3 Ørsted line width at 9.6 gigahertz. So this is already very small. It's among the smallest values published for thin layers. And the damping is 6 times 10 to the minus 5, which is the lowest value published for thin films. We don't know why it works, but it works. And so now the question is, can we combine these two things? Because now we have a process which works at room temperature, and this please no lift off is no longer valid. So, but there are a few questions. So first thing is, although PLD is a directed process, the question is whether it's really compatible to lift off. And because you really need nice lift off to get these structures. The second question is, I mean, we have shown that this stuff crystallizes over something like 500 nanometer from the substrate, 100 nanometer from the substrate homogeneously. But now we're talking about something which has a few spots where it's touching the substrate, and the rest is just connected via something like a micron of material. So will this still crystallize in a nice way? And the third question is, I mean, we know the layers have very nice properties, but they are on a substrate. If we have these freestanding structures, is the quality still the same, or is it worse, or is it better? So, and here is how we did the thing. I just want to emphasize a few things. So we're using standard PMMA. We just take a thick layer, and then we use low voltage exposure to expose the span of the bridge. Sometimes we also produce some kind of overhang. Then in principle you already have a cantilever. And if you use very low voltages, like for example 2.5 kV, then you only have a penetration depth of 170 nanometer. And that's a very strict limit. So you can increase the dose, you can increase and increase, but due to simple physics, the electrons cannot penetrate any further. So that means you can expose the top of your resist wherever you like. You will never get lower than this one. And also the sides, it's intentional that this is slightly tilted, because due to the scattering of the electrons, you get an undercut, which gives you this nice lift-off afterwards. And then you do high voltage exposure, where you go to the feet of the bridge, because 30 kV, they go 10 micron deep. So these are two completely independent processes, and after development, you get something like this. So this is the structure after development, and now normally you would evaporate metal and you can make your bridge. In our case, we use PLD and we make YIG. And you can already guess the shape, and you can see here this undercut is actually what allows us to do the liftoff in the end. Finally, you will also see that the word is not as perfect as it looks here, but still it's good enough for us. And now you just have to resolve the PMMA, and then the top just floats away. And this remains. And it's actually quite stable, even mechanically, as you will see. At that stage, it's amorphous. That was the big question. Now, if we now do the annealing, will it crystallize from here throughout all the thing? But the first question was, does the lift-off work? And it does. Yep.
Sorry, and the size of the height is like also, it's about the size of the thickness of a heat. How much you lift it up?
Yeah, I can, wait a moment, I can go back there. So this here can be, we have done between 50 and 200 nanometers already. And it just depends on how much you grow. Actually, you can use pretty thin films because it's not as ideal as this one. You get some bending over here. You will see it in the next picture. So this is what we get. These were more or less the first results that we had. And the top one is before the annealing step. And the bottom one is after the annealing step. And it looks as if the bridge is bent, but it's not. That's, the picture is misleading. It's actually these sidewalls which look as if the whole structure is bent. In the TM pictures, you will see that the center of the bridge is completely straight. So, and here you can also see that the liftoff is not as nice as it should be. So actually at the edges, the PLD is not a clear evaporation process. You also have some diffusion to the sides, which basically touch then the PMMA, and it goes upward. But as you also will see, this does not conflict with the magnetic properties of the structures. And you can see, so this is a very small resonator, 500 nanometers. The other one, this is 5 micron. So, yeah.
Are you going to say more about this special gig target? Like the morphology of that uneannealed film, the lumps and stuff, is that from large chunks of stuff coming off from the PLD?
So the target that we're using has been mixed up by Stefan Ebbinghaus, and he's basically just been using all the stuff that you have to mix together to get yig in the end. The surprising thing was that first we got a recipe from Munich, and he did some annealing and tried to get it as crystalline as possible. But in the end, it turned out that just having the mixture compress it is fine. But we know that the properties of each PLD system are completely different. For example, I've talked to other groups. For example, the Paris group, they have tried to do the same thing, and they don't get the nice quality after the annealing. However, on the other hand, the annealing, I mean, here we annealed in oxygen. We can also anneal in argon. It's the same thing. The important thing seems to be that you deposit in oxygen. If you deposit in argon, then you can anneal however you like. You don't get nice material. However, if you anneal in any gas afterwards, after growing in oxygen, you get the good material. Anyway, so but this is just how the things look from the outside. This is how they look from the inside. And as you see, so this is a cut through a bridge, and you can see it's pretty straight. At least it's you don't see this banding, which seemed to be there in the first picture. You cannot see here that the thing is really crystalline. However, I can tell you already that the span is almost monocrystalline. So that's why it's almost monocrystalline. This is in the center because during the annealing it starts to crystallize from here and from there, and somewhere these crystallization fronts meet in the center and you get a kind of stacking fault there. And also here, there you have a lot of strain, and there you have quite a number of defects. But the span itself is like a monocrystalline slab of yig. And as I said, we can also do higher than this. So this is almost 200 nanometer high. And there you can see the strain is much bigger, so there's tons of defects here. But still, the span is crystalline, but the defect in the center is now much worse. But it's really about the height. If we make it long, then the center is more or less like for the other short one. I mean, this is about 2.5 micron. So you can see that we really have a large choice, and we can probably design the mechanical properties of the system that we want to have in the end. No, that's so these samples were prepared for transmission electron microscopy using focused ion beam, and to protect them, some carbon was deposited. And as the electron beam, which leads to the deposition of the carbon, goes through the bridge, you deposit the carbon on top and on the bottom. So you have carbon here and you have carbon there. And anyway, so now we know that we have this nice property. And again, we have no visible bending due to the strain. And all these pictures were taken after the annealing process. And here you can see, by the way, there is again the same defect as for the first structure. So long bridges doesn't matter at all. And now the question is, how is the lattice orientation actually? Do you have a good relation between the substrate and the structure itself? And to check this, so we did some fast Fourier transform on different areas. So first we select different areas of the bridge for imaging. You don't see the frames here, but anyway, you can see that all these areas are monocrystalline. And then what we do is we do a fast Fourier transform of the lattice in that area. So we have put it here in different colors, and in different colors you can superimpose it afterwards, and you can see that there is a very small rotation between the different parts of the bridge. And if you zoom in, you can even exactly measure what kind of tilt you have. It differs from bridge to bridge depending on the strain, but usually the left and the right side of the bridge are tilted against each other between 0.5 and 3 degrees. And also each side of the bridge is tilted towards the substrate maybe by 0.5 to 1.5 degree. So there's not a lot of mismatch, and it's really the lattice structure from the substrate which is adopted and which propagates through the bridge, but due to the strain, you can imagine it crystallizes like this, and then it meets in the center, and that's why you have the defect, because you have a slight mismatch between the two sides. Yes, maybe you can even get a nice explanation for this one, because you deposit at room temperature, and now you go to high temperature and the thing expands. So, and then you would expect that it goes like this, and then it starts to crystallize, and then in the end you have a problem. So now, but anyway, what's more important for us is the magnetic quality. And first thing we did, because we didn't know what else to do, we just said we do ferromagnetic resonance using a coplanar waveguide. And as we cannot or could not do at that time, we still can't, measurements on a single bridge, we had to do lots of bridges. So we made an array of 8,000 bridges, nominally identical, 3,000 by 500 nanometers, so 3 micron long, 500 nanometer wide. And this is in the gap of a coplanar waveguide. This also shows you that these are mechanically stable because we have the array of bridges, and then we spin on resist, we do electron beam lithography, we deposit metal, we do lift off, and the bridges are still there. So we can do post-processing with these bridges. That's a good thing. And measuring these identical 8,000 bridges, we get a line width of the main resonance of 12 Ørsted, which is in principle not a bad value. It's not world record YIG, but it's a good value, and this is for 8,000 different bridges, or identical bridges, not for a single layer. So this means that either we have very similar bridges, or we have very narrow lines which are spread over a certain area, or both maybe. We tried to measure at different frequencies. It's not so easy because you saw we have several lines. At some frequencies they simply merge and we cannot separate them, but in the higher frequency range we got some nice values, and we can say that the damping that we have is at least 4 times 10 to the minus 4, which is already quite nice. So, and then came Georg Wolterstorff and he said, hey, I can do better than you. No, he didn't say this, but he said, I can do a very nice experiment, because he does scanning time-resolved Kerr microscopy. So basically, he can scan with a resolution of 300 nanometer and measure FMR with a time resolution of 1 picosecond with a frequency noise, phase noise of 1 picosecond. And this allows us to locally visualize the time development of the X or the Y component of the magnetization vector. My thing says it's 30 plus 5, huh? Yes. I thought my my timer says 10. Okay, okay, good. Yeah. So then I have to move a bit faster now. Okay, So he could look at this, and we see that we have a homogeneous mode. You don't have the uniform mode anymore. In small structures, you only have standing spin waves. So, but this is what is closest to the uniform mode. And at lower fields, you have the Damon-Eschbach mode. This was measured at 2 gigahertz. And at higher fields, you have these backward volume modes. We can go up to 6 nodes up to now. So these are measurements. This is again 3 micron length. And you want to know whether this is correct, what we measure here. So we did some simulation with MuMax3, where we basically did a single step excitation, and we look at the fast Fourier transform, and then we select the frequency. So it's a bit different, because here we vary the magnetic field, and the other one we vary the frequency. But you can see that it fits quite nicely. So they behave exactly as they should. And here you can also now do FMR on a single spot of a single bridge, and there we have a line width of the main resonance of the this quasi-uniform mode of 140 microtesla. So this is 1.4 Ørsted. So it's really very narrow. And the question is why this is the case. And here you can see it. If you look at different bridges, they come to resonance at different fields. But this is about 0.7 millitesla difference. But this fits the broadening of the line to 1.4 millitesla. And then you have the different parts of the bridge. You have the span and the post and the overhang. So this is kind of topology image. And you can see that here you have a variation of about 7 millitesla between this resonance and that resonance. And interestingly, this is what you see. Here you have the main resonance, and here you have something 7 millitesla apart. So this is actually the overhang, which you see. And we have also measured the damping, and this is why the diagram was so large in the beginning. So here are the values from the TR MOOC. You have the line which is very narrow, and the intrinsic line width at 0 field is 75 microtesla, so that means 0.75 Ørsted, and the damping is 2.4 times 10 to the minus 4. So this is really high quality stuff. And meanwhile, we have also improved the process a little bit, so we can not only do bridges, we can also do these square resonators. We can also do this table-like structures, so we can make disk resonators. And we can even get spin waves in there. So this is not a simulation, this is a measurement overlaid to the structure. And you can imagine that we can now play very nice games, and especially we can try to couple this to other things, because as I said, we can do lithography on the structures afterwards. We can integrate coplanar waveguides. We even managed to put metal lines underneath the resonators, so we can have very strong coupling in there. And yeah, so in the end, I can say we were very surprised. The first idea was just, let's see whether we get a bridge. Then we saw, yeah, we get a crystalline bridge. And then we found, yeah, and the material quality is really good. Yeah, and now we need to think about what we can all do with this. I already have a lot of ideas. But anyway, so the span is monocrystalline. That's the most important thing, because you saw the span of the resonance. And I don't know why this laser doesn't work. Now it's working. The crystal structure is adopted from the substrate. And you can accommodate in these resonators magnons with low damping and very narrow line width. And fortunately, the edges don't play a role in this one. And also the feet don't play a role in this one. It's just the span, which is high quality, where you want to have the resonance, and which will also have the mechanical resonance afterwards. Yeah, now the question, and we can do additive processing, or it is an additive process, which allows us to put the bridges wherever we want, together with other electronics. And the outlook is first try to couple to mechanical vibrations, and maybe at some point we can couple to qubits, or someone else can use them to couple to qubits, because I mean, we can do growth, we can do lithography, we can also do some characterization, but we cannot do everything. So if you have any idea what you can do with these structures, please send me an email. We are very open for collaborations, because for us it's easy to make these things, but our measurement capabilities are limited, and maybe we will start 1 or 2 new projects, but we will not start all the projects which you can do with this stuff. And let me just announce for the end, we have 2 open PhD positions in my group. One is on ultra-fast electrical characterization of giant magnetoresistance. In this case, this means beyond 50 gigahertz, approaching 100 gigahertz. And the other one is on the fabrication of spin Hall nanooscillators. And then finally, also, this is not this topic here, but maybe interesting for the people who are working on molecules. So the SPINOS meeting on spins in organic semiconductors will be held in August this year in Halle in Germany. And we have a nice list of invited speakers already. And here you can see the topics, and if you're interested, the abstract submission will open next week. Thank you very much for your attention.
Questions, comments? Yes, please, over here.
At which temperature do you do your anneal?
We have a certain window, so 800 to 900 centigrade.
Benjamin first. Then.
Have you already seen some signature in the FMR of the magnetoelastic coupling?
No. And the reason is that we have no idea where the frequency is, and you really have to do a very fine scan, and you know that it's much more difficult to do frequency-dependent FMR, so to scan the frequency rather than the magnetic field.
Olivier? Yeah. Thank you for outstanding work. I think it's going to open. This is a
Thank you.
great breakthrough in the possibility of heat. I just want to mention that when you have very narrow line width materials, measuring the line width versus frequency is kind of tricky to infer some, what corresponds to quality.
Hmm.
I mean, it's much better to just talk about pure line width, because when you have a lot of when you have very narrow line width and you have a lot of inhomogeneous broadening, when you measure as a function of frequency, you might have a very flat behavior, which has no correspondence to whatever the dynamic quality is.
I know, and I think yeah, you also see it in the paper. Sometimes you have very low damping or very low growth of the line width with frequency, but the intrinsic line width is very large. But in this case, I mean, the intrinsic line width is 0.7, and we can say that this is low damping. Yeah, sure, but I agree completely. So this is, by the way, also for the layers. This is an example where you have narrow lines and low damping. So.
I say that as a general because a lot of people, it's true in metallics,
Yeah.
but I think in garnet you have to be very careful with this frequency dependence of the line width.
Yeah, I mean, this, for example, would not be so telltale here. No. However, I would guess that it's as good as monocrystalline YIG, because the span is monocrystalline. No, I don't know. No, but I mean, it's a single crystal, and so single crystalline material normally is not so bad. But this is something that we have to investigate now. But probably you can get it from the papers on the coupling between magnons and phonons from Hong Tang.
What was the thickness of those bridges in 20
I think we are about 100 nanometers probably, but we're basically limited by time at the moment, because the deposition process is very slow, and if we want to deposit 100 nanometers, we take something like 4 hours maybe. But in principle, there's no limitation. We can also grow thicker than this. And that's also why I think that we will get the mechanical properties where we want them to be, because we can vary the length between few hundred nanometers and microns, and we can vary the thickness between 20 nanometers, 20 nanometers maybe a bit thin, but at least 50 nanometers to 200 nanometers at least. And so we're very flexible in that case. in times of focused ion beam, you can well imagine that you just cut it off from the substrate and put it somewhere else. But again, I would love to do it this way, because then again, if each of the bridges has to be transferred separately, it means if you wanted to do it for 1,000, you need probably something like 2 PhD students, and then they can write a thesis about transferring bridges.
Just a comment on this. I mean, people thought, yeah, you're right, but people thought that, for example, the limitation in thin films, for a long time people thought that the limitation of a line width of thin films, ultra thin film of Higgs, was coming actually from the GGG, from the fact that GGG is a paramagnet, and especially, I mean, there was this, the line width usually of ultra thin film of Higgs increases as you lower the temperature. But it looks like there's a recent work done by Kaiser-Slautern. Actually, it looks like that it's intrinsic to the Higgs, and so it's defect inside the Higgs.
Yeah.
Last question, please.
My question was basically very related to what that discussion is about. If these structures were directly on the GGG, how would they compare quality?
So we have made nanostructures directly on GGG, because obviously if you can do lift off for bridges, you can also make small structures, and there we also get to we get the damping, so the frequency dependence also corresponds to 2 times 10 to the minus 4. However, even for an array, we see 2 times 10 to the minus 4. However, the line width that we see is not as narrow as for these ones.